The next talk is by Pierrick, and he will tell us about GnuZero.
Thank you. So hi everyone. So I'm going to talk. So I'm Pierrick. Thanks for the introduction. So I'm going to talk about our tool. So it's GnuZero. So it's a compiler-based Zeroization static detection tool. So it's based on GCC. So first a bit of context maybe. So what's Zeroization? Well, Zeroization is the action to overwrite any sensitive data you might have in your program, such as password or cryptographic keys, with zeros or any other dummy values. And here you have a small C program where you can see that there is a password allocated on the stack. You read the password from a user, you use it, and finally you use the memset function to actually overwrite your password with 0. So you are zeroizing it, basically. And so when talking about secret, you also need to take into account what's called the secret dependency. So that means your secret, well, then might propagate to other variables during your program executions. So here, for example, you have a small function which has two variables. So the secret variable, which is secret by name, and the x variable, which is secret, which is dependent on the secret. And so even though you correctly zeroize the secret, well, at the end of your function execution, x remains on memory, and so its value still leak, well, might leak. And so zeroization matters because your secrets, well, you need to explicitly overwrite them. Otherwise, if any memory disclosure bugs happen, well, you can have a leak of them. So for example, in those vulnerabilities, so for example, Heartbleed, which is a quite old vulnerability now on OpenSSL, but more recent vulnerabilities, for example, such as on the KeePass password manager, but also on the GNU Linux kernel authentication module, PAM. And so in C program, to be able to erase your data, so to zeroize them, you have some requirements. And one of them is that you need that your data has to be programmatically accessible by your program. So that means that your variables holding those data, they need to be in scope first, but they also need to be accessible. So those data need to be accessible without undefined behavior, such as you cannot access data behind a freed pointer, for example. But beside those requirements, you also have some problems, such as the fact that compilers are quite aggressive regarding optimizations. And for example, they are more and more aware on memset-like functions. And so they might just remove calls to memset functions if they see that the variable you're using with the memset function are not read afterward. And so that's known as the death store elimination problem. But another thing is that the fact that, well, programmers are human beings, actually. So it's kind of easy to get it wrong. You can simply, well, forget to insert the zeroization mechanism or misplace it. And so in C, it's due to the fact that, well, zeroization is manual. So that's make it fragile and error-prone. And so it's true that there are some tools that exist, but so static analysis tool. But according to some surveys from both academic and industrial worlds, well, developers have workflow, so they have habits. And so if a tool needs developers to break their workflows, then it will likely refrain its adoption. And another point is that the diagnostic of the tool is important. So if a tool has a complex or a noisy diagnostic, it's most likely the developer will not lose time to understand the diagnostic itself, hence refraining the adoption too. And actually, those 2 points are usability issues if you think about it. And so we try to say, well, okay, so GCC is already part of the developer's workflow. And actually, its static analyzer introduced in 2020 already implements a quite nice reporting system, as we will see. Also, GCC, so the GSA, so the GCC Static Analyzer, is aiming for sound analysis. Hence, we developed GnuZero, which is a tool to automatically detect missing zeroization in C programs. So as I said, it directly integrates into the GCC compiler through its static analyzer, so the GSA. So we needed to modify its internal a bit to fit our taint model. But thanks to its position within the compilation pipeline, so the GSA position within the compilation pipeline, GnuZero is optimization aware, which leverages the detection of dead store elimination. And we focus on two related weaknesses, so the stack and heap-based derivation failure. And GnuZero will track sensitive data from its declaration to its end of lifetime. And so we still need to know what is secret because it is context dependent actually. So we designed two attributes. So there is the scrub attributes on one hand, which helps identify sensitive variables, so the variables that will hold your secrets. And also the scrubber attribute, which helps identify effective zeroization functions. Because the goal of GnuZero is not to verify the effectiveness of zeroization functions, but rather to detect if there are zeroization mechanisms in your program. And so GnuZero relies on the symbolic execution of the GSA and taint tracking to follow sensitive data across function calls, but also through named and temporary variables that might be created by the compiler during the compilation. And so it's interesting to notice that since we are at the really late stages of the hardware and language independent intermediate representation, in GCC, well, every variable might be in memory or in registers. So we do not make any distinctions between memory and register here. And so GnuZero will emit any warning if any value, sensitive value, reaches the end of its lifetime as being unscrubbed. So here you have a small example where you see on line 8 there is the foo function, which has a secret within the y variable. So that variable needs to be zeroized. You see that it's passed by address to the bar function, and finally on line 11 it's effectively zeroized through the zeroize function, which is marked as being an effective zeroization function. But the bar implementation is actually dereferencing its argument. And here you have the value of your secret, which is leaking in the stack of that variable, that function. And so here you have an output of the warning issued by GnuZero within an IDE, which is VS Code, thanks to the serif format. And so you can have here a glimpse of the diagnostic system of the GSA. So you can see that there are several steps, and each of these steps is linked to a location within your source file. And so you can see that the first step is the entry to the foo function, then you go to the bar function, and finally on step 6, your secret is leaking. So to be able to do that, we designed a taint model which is different from other tools, because we make the distinction between two kinds of variables, of secret variables or tainted variables. On one hand, we have the source variables, which are the ones that are explicitly marked with the attribute scrub. And those variables can only be destroyed by a call to an effective zeroization function. And on the other hand, we have the tainted variables, which are all the variables that depend on tainted data. And those can be destroyed, so their taint can be destroyed either by a call to an effective zeroization function, but also by assignment. So here you have a transition table of an assignment, depending on the state of the left-hand side of the assignment and the right-hand side of the assignment. So if the left-hand side of the assignment is in the state source, so if it's a source variable, so a variable marked with the scrub attribute, then we don't really care what's on the right-hand part. The new state of the LHS will remain a source. But if it's untracked or tainted, well, we will look at what's on the right-hand part, and this will define the new state for the left-hand side. But defining a taint model is not enough, because we still need to define a leakage model. And so we went for variable lifetime. So we distinguished between two different lifetime here. So we have the stack variables, so those are the variables that are tied to a function scope. So basically those variables need to be zeroized before your function returns. And on the other end, you have the heap variables, which can be more tedious because they might live throughout several functions. And those variables need to be zeroized before a call being passed to free or realloc, for example. And so if a sensitive value reaches the end of its lifetime as being unscrubbed, it's a leak. It's interesting to notice that GnuZero does not need program termination, which leverages the analysis of driver code, for example. And this is because the analysis is occurring during the symbolic execution and not afterward. And so, as I said, we needed to modify the GSA a bit. So here you have, for example, two variables, so the secret and the Y variable. So only the secret variable need to be zeroized. They both have the same assignment, so for the value 42. And on line 3, we want to know, well, is Y in the unscrubbed state? So that means, is Y waiting to be zeroized? And the answer should be no. But actually, the analyzer, so here you have a glimpse at its memory model. So it's mapping, it's actually a map between what's called region and S value. So you can see region as the memory cell holding your data, and the S value being the content of this memory cell. And so here you have both the secret region and Y having the same S value. And so when you're implementing an analysis within the analyzer, well, you're actually mapping the S value of that variable. So here we will tracking the state unscrubbed for the value 42. And so here, on line 3, when we will ask to the analyzer, well, what's the state of the variable Y, when it will look its S value and look within the map and say, well, this is waiting to be zeroized, which is a false positive in our case. So we modified the analyzer to also be able to associate states with the notion of region, so the notion of memory cell itself. And so to keep away our modification of the GSA, well, the GSA itself, so the GCC Static Analyzer itself, was really designed to track states, so to analyze pointers itself, rather than regions, so for example, integers. So that's what's here. So that means that it was meant to track for S values, because the memory model itself actually gives you a 3 points to analysis thanks to the model of the S value and the region. And so we tested GnuZero on different level. We tested it first with unit test to assess its taint model, our taint model propagation, taint propagation model, sorry. But we also ran it on the NIST Juliet test suite, so specifically the test for the stack and heap zeroization failure, and we had 100% detection rate. But we also ran it on different real-world code base, so different kind of code base actually, so with different optimization level. So we ran it on the libsodium cryptographic libraries, but also on the GNU Linux kernel crypto models, specifically the implementation of T and S, and also on the GNU Linux kernel, GNU Linux, the WPA supplicant driver. And we found some issues in the 3 code base. And so just to conclude, well, our work on GnuZero showed that, well, the analyzer, so GSA, is very suitable for analyze real-world code because we were able to analyze cryptographic libraries, but also non-terminated code, such as the WPA supplicant driver. And of course, we have some compile time overhead, but that one is tied to the countermeasure complexity of the code, and only in the case where warnings are issued by GnuZero, because the GSA is actually doing some past feasibility computation, but in a lazy way. So yeah, thanks for your attention.
Thank you. So we have time for questions. First one was here.
Thank you. My question is, how crucial do you think the placement of the analyzer in the pipeline is for detecting the important optimizations and missing things that might happen in the backend, etc.?
Yeah. Well, it cannot detect a thing happening in the backend because it's just at the really late stage of the middle end, actually. it could be really interesting to try to put it on the back end. So I think it might, so depending on the backend, actually, you might have some false positive, totally, yeah. But most of the, from what I saw, because I didn't dig into the backend of GCC that much, because it's quite complicated, but from what I understand, most of the optimization, so most of the dead store optimization are happening in the middle end. And so you have some optimization for certain architectures, but yeah. So in those special cases, yeah.
Yeah, I would assume the problem is not in the optimizations. The fact that the lower rings might not do easy things like zeroizing a variable by assigning to it is a bit edgy. I'm not sure it works most of the time.
Yeah, yeah, I'm not sure it works either. And also link time optimization is after again. So yeah.
If I understand correctly, for the stack allocated variables, you individually scrub the variables that are marked to be scrubbed, right? At the end of the function.
Yeah, if they are marked, yeah.
I was wondering what would be the overhead, at least for reasonably sized stack frames, just to scrub the whole stack frame at the same time, and then you can use a very optimized loop for doing that.
Yeah, well, there's actually an implementation for that within the GCC compiler. It's an attribute. You just have to put it on your function, and it will basically scrub all your stack in your function. I'm not sure if there is the same implementation in Clang, but yeah. Yeah. It might be doable, yeah. To do it yourself, I'm not sure, because if you do it yourself, you're yeah. Yeah.
Okay, so last question. Maybe the next speaker can already prepare.
At some point you mentioned GSA aims for soundy analysis.
Yeah.
What does soundy mean?
Soundy analysis is for neither sound nor complete, but rather go for something that is close to soundness without proof, or it might have proof. But in the GSA case, there is no proof at all. Yeah.
So let's thank Pierrick.